Even though we're going to be using the calculator today, the point is instead the idea behind the limit and how to solve. And the most important word of section 12.1 is approach. The most important word of section 12.1 is approach. So we were saying yesterday, this whole paragraph, in a sense, even though it's informal, this whole paragraph can be summarized in the statement right below the paragraph. In a simpler way, I suppose. And then that statement can be summarized as this statement, and this statement can be written with the notation, which you see right here. The limit as, this is literally what the, well, I guess, to be honest, I think the verbally is technically right here. The translation of this, in the sense of how you would read this statement, would be right up there. For instance, what do I mean by translation and the way of reading it? Well, what if I said F parenthesis X parenthesis? That's not how we should say that, right? It's technically what it would look like, F parenthesis X parenthesis. But how should we say this? A function F of the variable X, where there is a function F in terms of the variable X, or you could just say the simple way of saying it F of X, but you wouldn't read it F parenthesis X parenthesis, right? That's awkward, that's weird. So the same reason that we didn't read F of X as F parenthesis X parenthesis, we're not going to read this lim X arrow A F parenthesis X parenthesis equals L. No, that's awkward. That's horrible. Instead, we'll say, okay, when we see lim, we understand that to be a shortcut or an abbreviation of limit. The limit of who or what? Of F of X as what movement is happening, X is approaching A, is, if it exists, L. Now, a couple things real quick. F and L go together as types of values, and X and A go together as types of values, because if X is approaching A must be a similar type or a similar variable or a similar measurement. So therefore, X and A are both independent variables or independent values. So we could say X values, or denoting X values, whereas F of X and L are dependent vars, and so Y values. And you guys should know that F of X goes with Y and X goes with X. Like, that's pretty obvious, but what's the new, what's the different, what's the weird? L is a Y value. A is an X value. Okay? L is a Y value, and A is an X value. So, if you're given a problem, and it says find or solve for, or what is the limit as X approaches A of F of X, what kind of answer are we looking for? A Y value. Or you can think a height, if we're looking at a graph. A Y value or a height. Now the height could be up, the height could be down, the height could be a positive, the height could be a negative, the height could be a 0 for all we know. But we're looking at the heights. And the movement as to which heights we're looking at, we're going to be looking around as X approaches A, and X is that particular X value. So in notation, there's only one arrow. There's only one approaching, but technically, even though there is an equals, and this is where a lot of debate happened back in the day, even though there is a equals, technically, to fill in this equals, to say the limit is, the limit lands on, the limit actually converges and gets to L. The idea behind it is actually both the Y is approaching and the X is approaching. So we technically have the X is approaching a certain special X value. And we're trying to figure out if the Y's will approach a certain special Y value. In the debate, like, there were these monks that got into it, and the church got really mad. You guys know that when the church got mad, they started killing people. Anyway, church got really mad because they would say, wait a minute, the approach can't be the equals. The approach means what's going to happen, but you can't say that's what does happen. They got really mad. Think geocentric, heliocentric, that kind of mad. Yeah.
What does this have to do with religion?
Because their philosophy is infinitesimally close isn't actually landing on. And so remember the area problem? The area problem was all about the rectangles. And the rectangles, adding up a finite number of rectangles is an approximation, but they were like, no, we want the exact. I mean, this is a very gross simplification, but we want the exact. And so the whole idea of infinitesimals the church hated, and this is why. Because infinitesimals are making those rectangles infinitesimally thin. And they're saying, ultimately, you're accumulating these lines to get the area. Because if they're infinitesimally thin, there is no depth. In essence, you're making the depth go to 0. If the depth goes to 0, there is no rectangle. It's just a line. A line has no depth. And so this idea, they saw it as, I don't know if they saw it as mystical. There's a whole article on it that Dr. Neary gave me a couple years ago about how there was this whole debate between basically these monks, because they were the philosophical ones. In a lot of early math, there was a lot of philosophy tied with it because you were making these jumps in thought. But the idea of adding together the lines, they're like, no, that's impossible. You can't get something out of nothing. Funny, the church saying that. Anyway, but you can't get something out of nothing because they were saying you can't accumulate, you can't add up lines because there is no depth, so it's impossible. And so they thought they were kind of doing like this voodoo magic of being like, ooh, we'll make something out of nothing. And they're like, oh, blasphemy. Anyway. Gross simplification. I'll find you the article if you want to see it. Okay, so coming back. This one, still the idea of infinitesimally close, but instead of like the whole idea of area of accumulating infinitesimals to actually make an area. This one is you're just getting infinitesimally close. This is more to do with the tangent problem. But as you guys saw, limits are involved in both. Trying to going towards what we want, even though we can't physically solve once we get there, and saying, oh, but we'll know what's going to happen. You can kind of think through a few different implications as to why the early church might not have liked people making these jumps. You guys have already seen me talk about repeating decimals back when we did converging infinite series. Because remember on this one, technically this would have been 0.16 plus 0.006 plus 0.0006 plus 0.00006. Actually, a better way of doing this probably would have been 0.1 plus 0.06. There we go. We could have made this the infinite geometric series, but we wouldn't have stopped there because that technically wouldn't be the entire value 1/6. You would need to keep going forever, the repeating decimal. So the idea is that we can't have something infinite that is still contained because there is an infinite addition going on, but it's still contained in a finite sum. That's kind of an idea of a limit in the sense that you can't actually get to the end of this, but we can say, oh, I know what's going to happen, and it's going to be 1/6. You guys have seen, and I kind of talked about it back when we were doing the infinite geometric series, M.C. Escher's paintings in the sense of, this is a little bit different one, but it's very similar to this guy. In a sense of, you can count the fishes for a while, but then as he starts making the fishes smaller and smaller and smaller, kind of like this geometric sequence of adding smaller and smaller and smaller terms. The number of fishes approaches infinity, and yet it's bounded by a finite area. We could go into fractals, and that's where a lot of like CGI and different things like fields really took off when this new math was found in the 70s. Not new math, it's from an old book. But was it Benoit Mandelbrot? I forget how you say his name. But he was looking through an old textbook, and he was like, hey, wait, I think I can. And then that spark led to all sorts of really cool advancements in medical imaging and in CGI as well. But anyway, fractals still kind of seem to encapsulate the idea of infinite and finite because the perimeter of a fractal is infinite. As you keep zooming in, there are more iterations, and it keeps on breaking down. The perimeter is infinite, and yet, in a sense, the area is finite. Anyway, a few different cool ideas trying to further illustrate convergence.
How do you make those on a computer? Like, so
A fractal? It's a bit complicated. I would Google Julia sets. Yeah, Julia as in the girl's name, Julia sets. Or you could even look at the Mandelbrot, I think it's Mandelbrot? No, you don't say the T. He was something European. Anyway, you could look up his fractal. It's basically needing more parameters than we could possibly do in our calculator. And it needs to be kind of like if you think of the recursive sequence, how it builds on each other. There are different iterations that need to be repeated over and over and over again. So if you want to see a little bit more of the math, it's just beyond our scope, but look up Julia sets or look up Mandelbrot fractals. Or just Benoit Mandelbrot.
Can you make them into 3D?
Okay. So this whole idea of limits. Not necessarily yet going to infinity. That's what calculus needs. It needs us to get infinitesimally close to. Whether it's infinitesimally thin rectangles or infinitesimally close points of a secant line to make a tangent line. We're not doing that today. We're just trying to figure out the whole approaching idea and exactly how a limit works. Before we get crazy, before we apply it to calculus, just what's this notation? What's it talking about? And we're going to use the calculator to hopefully understand a little bit better. So we've been working with tables a little bit with like polar and parametric, right? We kind of got back to tables. We're going to, oh, hi. Oh, bye. Okay. We're going to get back to tables a little bit here, too. No, I just want you to go away. Okay. But we're going back to old school tables with x's and y's. I'm going to do x and f of x. And in the middle of the table, just for sake of illustration, I'm going to put a. Because I need x to approach a. And if you guys read the paragraph from the informal definition of a limit, you will see that x needs to approach a from either side. That x will need to approach a from either side. So I put a in the middle of the table so that we can come towards a from below it and come towards a from above it. Now there is some notation for that, and I'll show that as well. But the idea is we're going to need to approach a from below, think number line, from values to the left of a on a number line, and then from above, from values higher than a on the number line. But we're not going to necessarily be counting by ones, because if we count by ones, we're not going to get very close to it, to the value itself. We need to be taking smaller and smaller and smaller and smaller steps, or at least smaller and smaller and smaller subintervals to get closer and closer and closer to these. But from below, we could actually say that x is going to be approaching a from numbers a little bit less than a. We put an actual negative sign in exponent. It does not mean a power. It's notation for x going towards a using numbers a little bit less than, a little bit below a. And then this one, what do you guys think the notation would be? Just kind of process of elimination, or even just using similar logic? X approaching a, yeah, with a little plus. Numbers just a little bit higher. And what we're going to do is we're going to put a big old question mark here, because this is what we're trying to figure out. We're going to be looking at the y values, and we're going to be seeing, does f of x seem to be approaching a certain L from below and a certain L from above? And we're going to ask ourselves, do these two match? If they match, if they meet, if they agree, then we can say that the limit exists and the limit will equal L. So if L1 equals L2, then we can go ahead and say, yes, the limit does exist and the limit will end up equaling L. So it's all a discovery, it's all an exploration, it's all trying to figure out what's this approach thing do and how do we do it mathematically as far as with numbers, just basic numbers, not even talking about variables or quantities or any of that. Just numbers. How do we do the approaching with numbers? First of all, we do it from two directions. How? Okay, we'll get there, but we have to come from two directions, x coming towards a to find this limit, and then we're asking ourselves the question, what are the y's doing from below? What are the y's doing from above? And if they seem to be going towards the same place, we say, yay, they're in agreement, so done, the limit exists. If they're not in agreement, the limit does not exist. So let's take this example and try to make a table that uses these ideas for this specific example. So first of all, we have our x and we have our f of x. Second of all, what's going to go in the A spot in the middle of our table? Because it's x approaching A, or 2. So I'm going to have x come towards 2 from numbers a little bit below, and I'm going to have x come towards 2 from numbers a little bit above. Just notation. Now, a little bit below. Question, is negative 10 a little bit below? No, I don't want to plug in negative 10. Oh, okay, negative 1, is that a little bit below? Not really. It's below. It's not a little bit. How about 1? Yes. Getting better. Can we do the whole cold and warm thing? You were really cold at negative 10. You were barely warmer at negative 1. A lot warmer at 1. What's something even closer? Ooh. Let's go 1.9. Let's go 1.99. Let's go 1.99. How can we get even closer? 1.99999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999. Now, before we go to our calculator, hold on, pause. We need to come from the other direction. Is 10 above? Yes, but is it a little bit above? Nah, you're cold. Ooh. Now, you might not want to start at 2.00001. Maybe start at 2.1. How do you get closer? Now, some people would say 2.11, 2.111. No, you're staying farther away. How do we get closer? 2.01 and 2.001. How would you get even closer? 2.000000000000000. But at some point, it's kind of silly because the calculator will round anyway. Now, how do we actually do this? Could we, in our calculator from our home screen, could we be super cool and be like, we'll plug in every single one? I suppose we could plug in every single, that's not you guys, 1. We could do 3 times 1.9 plus, nope, minus 2. Okay, but wouldn't you have to keep on, like, I don't know, going back and stealing and then going and deleting and then inputting a new one? Ugh. So what's better? Realizing there's a pattern to this. Every time you'll be taking a quantity, multiplying by 3, and subtracting 2. Where do we put patterns in our calculator? Yeah, we can put it in y equals and say, hey, I have a pattern. Can you deal with this pattern? I have 3 times the variable minus 2. You're like, cool deal. Could you, oh, too many x's. Could you go to the graph and could you say, hi, Mr. Graph, can I go ahead and have, you could do second trace value or just hit the trace button. It's a shortcut. And do 1.9. Yeah, I'm zoomed in. Sorry for my calculus problem. You can be in Zoom Standard. You do the same thing. It would still be on your window. You could find 1.9, and then you could do it again, and then you could type 1.99. Oh no, I didn't write down 1.9. Where's a cool place where you can keep all this info together and you can refer to it later, and it doesn't just, hey, go to your table. Oh no, but tables are going by ones. Have you guys ever actually read this little note if it comes up on yours? You can have it go by something different than ones. You can have it go by, oh, to get to 0.9, couldn't I do maybe go by 0.1s? Yay! Ugh. Well, maybe I should go by 0.01s. Uh-oh, is this going to get worse? How long are you going to have to scroll for? Okay, so forget that. Don't go by 0.1s or 0.01s because we're taking smaller steps as we get closer and closer to a quantity. So therefore, I don't think we want it automatically generated at all. So how do I change it, honors kids? Second window, good. Can't we change it to ask us instead of automatically generating values? And couldn't I put in whatever the heck I want? And couldn't I say, sweet, 1.9, got it, 1.99, got it, 1.999, got it. Now, just for sake of argument, We'll come back to that in a second. What did the y's seem to be doing? Increasing, true, but increasing by smaller and smaller steps. Do you think maybe the y's are converging to a set value? Looks like it to me. If we were to plug into our table, we could go ahead and say, all right, so we have 3.7, 3.97, 3.997. What if we added on another 0.9? 0.999, no wait, 999, there we go. I think it'd be 3.9997. So what do you guys think about the jump, the limit as x approaches 2 just from below? Does it look like 4? I think so. Now, if you want to go ahead and just for the sake of argument be like, okay, I want to see what's really going on, I'm going to put all kinds of point. I've said way more than I've typed, but it's okay, my calculator's lame anyway. Go! Ah! What happened? But why did it round? It's a calculator. It didn't round. Why? Oh, it can't fit them all in. So instead of doing 1.999 ... it just rounds it. So it looks like 2, but is it 2? No. Am I still approaching? Yes. But it hits 4? Nope. Oh. What happened? What if I hadn't gone quite so crazy? And what if I had done a few 9s? What if I had done a few more 9s? What is it doing over here? It eventually ran out and then it had to round this guy. So technically when you're approaching, we're not looking at the at, we're looking at the approach. And as we approach, what seems to be happening from below? It's going to 4. What's it? The y values. The function seems to be going to 4. Now, go ahead and clear all these guys out. Clear, 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 clear. Now let's come from the other direction. Let's do 2.1. 2.01, 2.001. If you want to be snazzy, 2.000000. Okay, don't go too far because as we can tell from all of our rounding, there's only so far we can go before it has to round. But guys, as we look at these values, what seems to be the limit as you come just from above? Also looks like for me. So what did I say up above? If L1 and L2 match, if the limit from below seems to, or does, equal the limit from above, what can I say about the limit? 4. Now, why am I not plugging it in? I guess I could plug in. Have you guys tried plugging in 2? What happens when you plug in 2? The limit is, not the limit, sorry, the function is 4. F of 2 equals 4. Huh, I wonder if that always works. That would be a whole lot shorter than going to a table. Pause, do you guys hear what I just said? Did anybody plug in 2? 3 times 2 is 6, 6 minus 2 is 4. Huh. Plug in 2, you get 4. And that's what the limit seems to have been. I wonder if that always works. That'd be a lot shorter. Remember, we're not doing the calculator work in order to be good at the calculator work. We're doing the calculator work to get down the idea of approaching. So, this is what we already found. Technically for a limit, we wouldn't have solved that guy at all. For the idea, for the concept, we would have just looked at the approach and said, hey, looks like 4, sweet, they're in agreement. Let's call the limit 4. And what the graph looks like, please go ahead and sketch the graph. What the graph looks like is as I'm headed towards this x equals 2 on the function, so I go up to the graph and I say, okay, I'm going towards. Looks like I'm going to 4. As I'm going towards, looks like I'm going to 4. Since they both agree, as x approaches 2 from below and above 2, the y's seem to be going to 4 from below and above 4, so I'll say, sweet, yes, my limit exists and my limit is 4. And what happened when you plugged in 2? You got 4. So you were approaching a filled-in point. want you to think of it like this. Two guys, two separate cars, traveling on a road. Call one red, call one green. Sure. As the red one comes towards, I'll only have the red one come from below. The breakfast spot they're supposed to be meeting. You're coming to a diner, wanting some breakfast. Sit down, talk about life, okay? As the red guy comes towards the intended meeting spot, he's going. He parks and he walks in the diner and sits down. He's there. But where was he headed? To this diner. Blue guy. I changed it to blue. It's a prettier color. But yes, I did say green, Lo siento. And tomorrow's Patriotic Day. Anyway, so as we approach, the blue guy also coming to the intended spot. No big dealio, right? He parks his car, he walks in, he sits down, he's going to have breakfast. Were they headed to the same spot? Yes. Are they going to have breakfast? Yes. It's a good day. Okay? So, blue car, red car, coming two different directions on the road, headed to the same place, and they were able to go in, sit down, and have breakfast, and it was great. Okay. Is that how it always happens? No. Ready, set, go. Ready, set, go. It's not about the calculator. It's not even about the decimals. It's about the idea of approaching. Hang in there. Yes, there are shortcuts to solving, but this is about the idea. And as I mentioned, AB kids, after a full year of calculus, still getting stuck on some of the concepts of limits. Feel free to collaborate in your groups. You guys are trying to make a table, trying to plug into your calculator. You guys done? All right. Put the A in the middle. Put the function in the calculator. All right. I'm just slowly starting. There's a hole. Ooh, you guys are smart. Look at you guys go. There's a hole in the bucket. Dear Liza, dear Liza. There's a hole in the bucket. Dear Liza, a hole. P.S. This one's still pretty easy. What? Okay, so you put the function in, you went to your table. What did you guys start typing in? Negative 3.1? Look at you guys go. Because x needs to approach negative 3 from below. A few people had a little bit of trouble with the negative numbers, trying to think below. But on a number line, here's our negative 3, here's our negative 4, and here's our negative 2. To come from below, I need to go a little bit past negative 3. It's negative 3.1, negative 3.01, negative 3.001. That's different than the other one because the 001s were on the other side. These are negative numbers. Does that kind of make sense? So then what would be on this side? I'm coming to you, Colby. Hold on. What would be on this side of negative 3? Negative 2.9 and negative 2.99 and negative 2.999. Do you see the visual as to what's above and what's below with negative numbers? Some of you guys went to your calculators, coming from below, coming from above. Coming from below, I'm just going to plug in negative 3 because last time it was good. Ah! It is undefined because when you plug in, you get 0 over 0, which does mean it is a whole. Anyway, I have negative 0.1639. I have negative 0.166 something something something, and negative 0.1666 something something something. Huh. It sure looks like it's converging. Then why is there an error? But if I'm doing a limit, am I looking at the at or at the approach? For a limit, am I looking at the at, what's going on at negative 3? Or am I looking at the approach? Because didn't we write just a second ago that a limit is answered by, that was the debate of why there was an equals and not an approach. The limit is, or the limit equals, what is being approached. So I'm looking at the approach. So guys, what seems to be, oh, hey, did you notice that I wrote down what 0.166666666 is? What seems to be happening as I come from below, holy cow, let's go, from below negative 3? Well, it sure seems as I come from below negative 3 that this thing is approaching 1/6, negative 1/6. Negative 0.166666666. What ended up happening is you guys came from the other direction. Does anybody have what the value was at negative 2.9? How about the next one? How about the next one? What seems to be happening as I come from above? What does the function seem to be approaching? So what is the limit? If L1 equals L2, what do I say about the limit? It exists and it is the value that's there. No, the function doesn't exist there. The function has a hole. I'm not caring about the at, I'm caring about the approach. As x gets closer to negative 3 from above and below, what are the y's getting closer to? And I answer the limit equals with what is being approached as long as L1 equals L2. Graphically, what's going on? Let's go back to our diner. If I have a picture, and if I don't, we'll go back. Nope. our diner on this one. We'll see if you guys can figure out why the graph is what it is. What was the function? So limit as x approaches -3 of x squared minus 9 all over x plus 3. Okay. We'll talk about how I got the graph in 1 second, and no, I did not have it memorized. Okay. So, there's an asymptote. Who cares? What am I looking at, or where am I looking at? Just kidding, I'm not looking at, I'm approaching, but okay. So I have my -3. My red car. Last time he was coming from below, right? Okay, so my red car coming from below -3. Where's the road to the left of -3? Right here. So he's coming. He's coming. They're supposed to meet for breakfast, right? He's coming, he's coming, he's coming, he's coming. Where is he headed? This location of the diner. He gets in, up to the door, pulls on it. It's locked. It's one of those small family-owned ones, and they took the day off. Oh. Is he going to have breakfast? No. But is he there? Yes. Blue guy. Coming from the other direction. On the road, headed, parks, gets in, up to the door, tries it. It's locked. Is he going to have breakfast? No. But were they headed to the same place? Yes. Was everything good until they went to open the door? Yes. Did they meet? Ooh, there's a dilemma. We're not answering that question, but what we are answering is, does the limit exist? And the answer is yes. Why? Because they both headed to the same place. Some people would say the diner burned down, so they went and they tried and it wasn't there. But they were headed to the same place. Either the diner burned down or they got all the way up to the door, which is a little bit more accurate, and it's right there. The burned down is kind of like there's a huge, and you were a little ways away from it. But anyway, either way, the limit exists and the limit equals 1/6, -1/6. The limit is what were the y values headed towards. They were headed to the same place. The limit is technically talking about the approach. The limit exists, and the limit is -1/6. Make sense? Did they get breakfast? No, so it's kind of a bummer. We would say this function is not continuous. However, the limit does exist. Pause. Can anybody figure out how I got this function? I said he is the same guy as this, as long as I say x cannot equal -3. This is a rational function with a vertical asymptote at 3. We've talked about the 1 over x being of the general form of... I canceled out the plus 3. So the x minus 3 remained. This is because I canceled out the -3. The domain is x technically can't equal plus or minus 3. But the function still shows that x can't be positive 3. I had to write x also can't be -3 when I canceled it out. This is additional to the natural function. 1 over x normally looks like, zoop, there it is. That's how I figured out that part. No! How did I figure out the whole was at -1/6? By the limit, but how could I have done it mathematically? What if this was okay? I would plug him in there, and I would say, if it was okay, 1 over -3 minus 3 is -1. Maybe there is a way to find it with math and not with our calculator. If it did work, if I didn't have to cancel out and say it didn't work, It would have been right there. P.S. I also did a quick little horizontal asymptote action in my head saying that the bottom wins, the limit is 0, so I knew this had to be going towards 0. That had to be going towards 0 as well. How I graphed the function. Okay. So, graphically, we've kind of been building up to graphically. We played with our calculators a little bit. Graphically, still kind of keeping it basic. If we're looking for a limit approaching on a graph, we're going to have to approach from the right and the left of the x. From the right and the left of the number x is approaching, aka, didn't we call him a? So we're going to have to come from the right and the left of a, looking at the, well, if I want to find the limit, aren't I looking at the y values? I'm going to approach on the graph from the right and the left of the number x is approaching, looking at the y values and asking myself the question, are my two drivers approaching the same location? Whether or not they're going to get in and get breakfast or not. Are they, in a sense, going to meet? That's a hard question, but are they headed to the same place? Are they going to be in the same parking lot? Are they going to be walking up to the same diner? The answer is yes. Will they have breakfast? Sometimes yes, if it's open they can get in. Sometimes no, if they get all the way there and then it's locked. But the question is, are they headed to the same place? And the limit is asking the height of that place. So this graph down below, I have not given you a function. You cannot put it in your graphing calculator. However, I've given you everything you need to know to be able to answer the limit question. The problem down below, I did not give you a function. You cannot put it in your calculator, but I've given you everything you need to know to answer the question. Does the limit exist? Yes or no? Do they agree as to where they're headed? Yes or no? Good. The limit does exist. And if the limit does exist, what does it equal? The limit. The limit of f of x as x approaches 1, or the y values, the f of x values are approaching what as x approaches 1? 2. Why? Because whether you go from below, the y values are getting closer to 2, or whether you come from above, the y values are getting closer and closer to 2. Sorry, anyone on the video who was just listening. Okay. Whether you go from above or whether you go from below, the limit does exist. So here's my question. First of all, let's see how much is left. Ooh, let me freeze the screen real quick. You guys, what's the limit of this problem? What's the limit of this problem? It is 2. Why? Are they getting breakfast? No. But are they headed to the same place? Yes. So what's the limit? The approach, not the at. It's not answering the breakfast question. It's answering the whether or not they're headed to the same place question. Okay. So then that begs the question, when does the limit? Girl fans, come back tomorrow. Everybody else, homework's not due till Friday. All right. Ready, set, and see you guys later. Bye. Yeah.
Okay, so when I was plugging in the value